Hi everyone. Today I'm going to be talking about MOSFETs. So if you haven't checked out the previous video, so I was talking about BJTs, characteristics of BJTs and everything involving BJTs. So a MOSFET, just like a BJT, is a normal transistor. So we have two types of BJT transistors, so NMOS and PMOS. So those are just like simple configurations, but then we're going to explain the fundamentals and the physics behind MOSFETs in this lecture. So NMOS, an NMOS doped transistor is actually like a negatively doped transistor. Just like we talked about like silicon being used to make transistors before, they dope silicon with electrons. So when you dope silicon with electrons and then it's got like more of electrons than protons, then we call it an NMOS device. Then if you actually dope with more of like holes or positive charge with respect to negative charge, is called a PMOS electrode. And then how it actually works is that we have a gate, and then like this is how it's actually built. It's like the general structure of a MOSFET. Then we have a drain, we have a gate, we have a source. So initially I'm going to only talk about like what happens when the gate changes and what happens like at the source and the drain. So basically what happens is that this is a p-type doped silicon and this is an n-type doped silicon. That's also an n-type doped silicon. But now at the gate we actually have voltage applied there, and that is what actually controls what happens here. So at this point there's going to be a change here when this thing changes. This is going to be okay, assuming let's apply a positive voltage here. So if you apply a positive voltage at the gate and this thing is actually positive, you know that like positive charge repels positive charge. So the protons here are going to be pushed all the way down towards the bottom of the structure. And what's going to happen at the top is that this will become visually negative. Since we have an n-type here and an n-type like dope, so it means we actually have more of electrons there. There's going to be a channel here which will be created and which will actually be negative with respect to P. So that kind of opens a channel and makes this thing conductive. So, but it's going to be conductive only at this point, and the size of the channel will differ depending on the value of G. So when you vary the value of G, when G increases in terms of voltage, the space will actually also increase and widen, but if it's a small voltage, it will also decrease. But if you look here, we have this structure, and this is called an insulator. The reason why we need an insulator is because we want to have a capacitive charge, and capacitive charge just means that we're going to use electric field to actually switch this thing on. So we don't need contact. As long as there's like an electric field here, this thing can move. So what's going to happen now is that there is going to be a small voltage which we should overcome before these things or the electrons here start moving, before the protons start moving. So that little bit of voltage is called VTN, it's called a threshold voltage. Now, I have drawn a structure here showing like a PMOS device connected, an NMOS device connected. So I put VDD here, I put VG here with the positive and negative terminals connected. I put the gate there, and you can see here I've got positive charge over this point, at this point. And here I've grounded this, I grounded like the source. So initially I had positive charge, but then when you look there, you can see that there are electrons, and these electrons are just, like I opened a channel, and when I applied the voltage, this channel went down, and then there was a channel where electrons could flow over there. And this is basically how this thing switches this thing on and off. So basically we have a terminal, we have a terminal. So there's something you want to do with the drain and the source. There's a reason why I put the voltage there, but right now I was just explaining the on and off operation of the MOSFET device. Okay, this channel is called an inversion layer because normally it's actually a p-type and is positively charged, but the moment you apply a positive electric field, the positive charge goes down and then this becomes a negatively charged channel. So we call it an inverted channel. Now let's assume that we apply VDD. Let's assume that I apply VDD. When I apply VDD on this thing, what is going to happen is that it's going to push electrons from the negative channel there to this negative channel, from the drain to the source. So the electrons will flow through this channel and go there. But because I said that the thickness of this channel here will differ based on the value of Vg, depending, let's assume that Vg now is kept constant, meaning we actually have a specific size of this thing. So depending on the VDD channel over there, so let me just make a line here so like it's nice and straight. So let's say the channel size is this much now because of a specific value of Vg. Now, when you actually now push voltage here, it's going to push electrons from here to this channel, but then the value of the electrons and the size and the speed of the electrons will depend on the size of this channel. The bigger the channel, the more the electrons, the smaller the channel, the smaller the electrons. Basically, we're talking about current. So the speed will decrease if there's more friction, and if there's openness, the electrons will move freely. So now at this point, we have actually just talked about an on and off operation of a MOSFET device. Let's say now, okay, like in this model, as you can see, there's no resistors whatsoever. It's just like a voltage source in a MOSFET device. If there is no, like in this terminal, assuming that Vg is constant still, if in this terminal we did not plug in any resistor at any point in here, we are going to actually have VDD being equal to VDS. And now let's define a new voltage. VDS is the voltage between the drain and the source. So the voltage here is VDS. This voltage is the voltage dissipated in the transistor. So VDD is the voltage that you're supplying, and VDS is the voltage that is dissipated in the transistor. When you put a resistor here, or in series in this link here, is going to have a voltage, and the voltage that is going to be in that transistor, in the resistor, is going to be equal to VR, and VR is going to be equal to ID multiplied by VDS. VDS minus VDD. So since the voltage going through the resistor will be a potential difference of the voltage in the transistor and the voltage and the supply voltage, you're going to have like a difference voltage going into there and the voltage going to a transistor, and then from there you're going to actually have a specific amount of current flowing through this. So the amount of current, which is ID, which flows from the drain to the source, is determined by Vg, and from there, if you apply current here, so if you apply a voltage source here, the voltage source will push electrons down the path here, and then the electrons also and the current here will also be determined by the value of VDD. Now, Vg and VDS, just like I've mentioned here, have different polarities. Basically, from this point to this point, there is a polarity gradient. So actually, what I'm trying to say is that like on this negative side, there's going to be a positive gradient, and on the left-hand side, there's going to be a negative gradient. So since this part is connected to the negative terminal and this to the positive terminal. So, but we know our gate all over this whole region is positive. So what is going to happen now when you apply a voltage here? The inversion layer which we talked about here is not going to remain the same. So because of the positivity on the side, when VDD increases, the more VDD increases, it becomes more positive, and then it makes this side to pinch, because we need this thing to actually be pushed down. But then because of the positivity here, it repels the electrons, and then pinches this layer over there. So because like we need a specific voltage here, which is actually VTN, to have electrons flowing here. So when Vg stays constant and VDS increases. Now, as VDS increases to be more than Vg plus VTN, what is going to happen is that this thing will close up completely, and then there won't be any electrons flowing. So if I have to repeat what I said now, I'll say that when I'll say Vg should be VTN more than VDS for this channel to be open. So, but like when Vg plus VTN is less than Vd, this thing is going to be completely closed. And when this thing closes up completely, we say the transistor is in saturation. Now, what's going to happen when this thing's in saturation? The electrons won't stop flowing. There's going to be a jump of electrons. So the electrons will jump from this channel to this channel without any control, because now there's no voltage controlling how much of the electrons flow. So in that state, we say the transistor is in saturation.